7 minutes. That's how long it took for a signal, already ancient by the time anyone on Earth saw it, to cross the gap between a dying spacecraft and the only home it would never see again. On September 15th, 2017, a machine the size of a school bus sent back a handful of final photographs, and then it did something almost no other spacecraft in human history had ever been ordered to do. It flew straight into a planet on purpose and let itself be destroyed. But here's what almost nobody talks about. The pictures weren't the ending. They were a message. And it took scientists years to realize what that message actually said, because buried inside data Cassini beamed home before it burned alive in Saturn's atmosphere, researchers are still finding things today, in 2025 and 2026, that are quietly rewriting what we think we know about life beyond Earth. This isn't a story about a spacecraft that died. This is a story about a spacecraft that is still talking. To understand why those last images matter, you have to understand what Cassini actually was, and what NASA was so afraid of that it chose to kill its own machine. Cassini launched on October 15, 1997, carrying with it a European probe named Huygens, and it did not arrive at Saturn until nearly 7 years later, in the summer of 2004. 13 years it spent in orbit around the ringed planet after that. 13 years of flybys, of storms photographed in impossible detail, of moons that turned out to be nothing like what anyone had predicted. But by 2017, Cassini had a problem, and it wasn't a problem you could fix with an upgrade or a patch. It was running out of fuel. Think about what that actually means for a spacecraft orbiting a giant planet surrounded by dozens of moons. A healthy spacecraft can correct its own course, it can dodge, it can adjust. A spacecraft with no fuel left is a blind object on a fixed trajectory, and eventually, inevitably, gravity decides where it goes. Not the engineers on Earth, not NASA, not anyone. And that is where the real tension of this story begins, because Cassini wasn't just going to run out of control near any random patch of space. It was going to run out of control near Enceladus. Here's where it gets worse. Enceladus is a small, icy moon of Saturn, barely larger than the width of a mid-sized country, and by the time Cassini's fuel gauge was ticking toward empty, scientists already suspected something extraordinary was happening beneath its frozen shell. In 2005, more than a decade before the final plunge, Cassini had flown past Enceladus and detected something it wasn't specifically built to find: plumes. Towering jets of water, vapor, and ice erupting from cracks near the moon's south pole, blasting material out into space at speeds that suggested they weren't coming from a frozen, dead world. They were coming from somewhere with liquid water, somewhere with heat, somewhere that, by every definition scientists use to search for life, was suddenly one of the most interesting places in the entire solar system. And that is the moment this story stops being about a spacecraft and starts being about a decision. Because if Cassini, out of fuel and out of control, drifted into Enceladus and crashed, it wouldn't just be an accident, it would be contamination. Earth microbes, hitching a ride on a machine built decades earlier in a clean room that was never designed to be sterile enough for a mission like this, could end up smeared across the surface of a moon that might already harbor its own biology. NASA's planetary protection rules exist for exactly this scenario, and the agency was not willing to take the risk. So mission planners made a choice that sounds almost poetic when you say it out loud. Rather than risk contaminating a moon that might already be alive, they decided to kill their own spacecraft first. Read that again. NASA didn't lose Cassini. NASA executed it, deliberately, precisely, on a schedule planned years in advance specifically to protect a place scientists hadn't even fully explored yet. This is not chaos, this is strategy. By April of 2017, the plan was already in motion. Engineers used a final close flyby of Saturn's largest moon, Titan, to bend Cassini's orbit using nothing but gravity, no fuel required, and slingshot the spacecraft into a completely new kind of trajectory. For the next 5 months, Cassini would perform something NASA nicknamed the Grand Finale: 22 separate dives through the narrow, roughly 200-mile gap between Saturn itself and the innermost edge of its rings. No spacecraft had ever flown through that space before. Nobody knew for certain what was there. It could have been debris-filled and lethal. It could have destroyed the mission on the very first pass. But Cassini went anyway, week after week, threading a needle no engineer had ever threaded, gathering data that would have been impossible to collect any other way. Think about what that decision reveals. A machine with almost nothing left to lose was sent into the single most dangerous, least understood region of the entire Saturn system. Not out of desperation, but out of calculation. Every dive was scientifically deliberate. Every risk was accepted in advance. This was a spacecraft being spent on purpose, like a resource nobody wanted to waste by letting it simply run dry in some empty stretch of space. And then came September. By September 11th, 2017, Cassini made its final close approach to Titan. The flyby engineers called the goodbye kiss. because its entire purpose was to use Titan's gravity one last time to bend Cassini's path downward, committing the spacecraft to a collision course with Saturn itself. There was no turning back after that maneuver. From that point forward, Cassini's fate was fixed. Whatever happened next, it was going to end inside the atmosphere of the planet it had spent 13 years studying. But here's where it gets worse, and where most people who've heard the basic story completely miss what actually happened next. Cassini didn't just quietly drift toward its death. In its final 72 hours, it turned its cameras outward one more time and began photographing everything it could reach. Not for engineering purposes, not because mission control needed the data, but because the scientists behind the mission wanted one last look. Linda Spilker, Cassini's project scientist, would later describe these final photographs as entries in the mission's scrapbook. On September 14th, Cassini's cameras captured their final pictures, the last entries in what Spilker referred to as Cassini's scrapbook. Popular science. Picture what that actually looked like from the spacecraft's perspective, if a machine could have a perspective at all. On September 13th, 2017, Cassini captured a haunting image of Enceladus, lit only by reflected light from Saturn's rings. The moon that had driven the entire final chapter of the mission, the moon whose hidden ocean had forced NASA's hand, whose plumes had reshaped the mission's ending, was one of the very last things Cassini ever looked at. As Cassini dove toward Saturn, Enceladus itself appeared to be setting behind the planet in the frame, slipping out of view just as the spacecraft that discovered its secrets was also disappearing. NASA, science, popular science. Then Titan. On that same day, September 13th, Cassini's narrow-angle camera captured views of Saturn's giant moon Titan, a world so strange that Cassini's own discoveries had already confirmed it had lakes and seas, not of water, but of liquid methane, an alien hydrocarbon ocean unlike anything else in the solar system. Titan is larger than the planet Mercury. It has weather, it has seasons. And thanks to Cassini, scientists now understand it as one of the most Earth-like and most bizarre places we've ever studied up close. NASA science. Then the rings. Cassini photographed Saturn's outer A ring, capturing the small moon Daphnis and the waves it carves into the edges of the Keeler Gap. A moonlet barely 5 miles across, somehow powerful enough to ripple an entire ring system just by passing through it. In the same final stretch of images, Cassini captured a lone propeller feature in the A ring, one of many structures created by tiny embedded moonlets attempting and failing to carve clean gaps in the surrounding ring material. Even in its last hours, the spacecraft was still finding new things to show us, still cataloging a system that, after 13 years, had never stopped surprising the people studying it. NASA science. NASA science. And then, the very last frame. The final image ever taken by Cassini's cameras is a monochrome view looking towards Saturn's night side, lit only by reflected light from the rings, showing the exact location where the spacecraft would enter the planet's atmosphere hours later. Think about what that means. Cassini's last act as a functioning camera was to photograph its own grave. Not metaphorically, literally. The final image is, quite plainly, a picture of the spot in Saturn's clouds where a piece of human engineering was about to cease to exist. That image was taken on September 14th, 2017, from a distance of about 394,000 miles from Saturn, and it shows the precise point where, a day later, the spacecraft plunged into the planet's atmosphere. NASAScienceSpace.com. What most people are not seeing when they scroll past those images or watch a 30-second recap online is what happened immediately after the cameras stopped. Because the story doesn't end when the pictures stop coming. It gets more intense. Even as Cassini made its fateful dive into Saturn's atmosphere, it kept transmitting new data home in real time. The imaging cameras were done, but Cassini had other instruments still running, still working, still doing the only job left available to them. And the most important of those instruments was a mass spectrometer, a device built to directly sample and analyze the chemical composition of whatever gas surrounded it. Key measurements came from that mass spectrometer, sampling Saturn's atmosphere and reporting its composition all the way until the moment contact was lost. NASA science. NASA science. Think about the physics of what that actually required. Cassini's small thrusters had to fight to keep the spacecraft's antenna pointed precisely at Earth, across roughly 900 million miles of space, while atmospheric drag from an alien gas giant was actively trying to tumble the spacecraft and rip it apart. It sent science data for as long as its small thrusters could keep the antenna locked onto Earth, and soon after, it burned up and disintegrated like a meteor. Every second that antenna held steady was a second of science. Humanity would never have gotten any other way, and every one of those seconds was borrowed because the spacecraft that was providing them was actively dying as it did it. NASA science. This is where the story most people know ends. Signal lost, mission over. A control room full of engineers, hugging, crying, watching decades of work conclude in silence. The Cassini team is remembered cheering, hugging, and crying after receiving the final signal indicating the mission had come to an end, with the spacecraft disintegrating in Saturn's atmosphere. That's the ending everyone remembers. That's the ending that gets replayed in documentaries and tribute videos. Space.com. But that is not actually where this story ends, and this is where everything changes. Because Cassini didn't just send back pictures and atmospheric readings in its final hours. Across 13 years in orbit, it collected an almost incomprehensible volume of raw data using a dozen different scientific instruments, much of which nobody had time to fully analyze while the mission was still active. Spacecraft don't get to slow down and reflect. They just keep collecting. And when Cassini finally stopped collecting in September 2017, it left behind an archive so massive that scientists are still, right now, in 2025 and 2026, digging new discoveries out of data, a dead spacecraft gathered nearly 2 decades ago. This is the part of the story that almost nobody tells, and it's the part that actually matters most. Go back to that final image of Enceladus, glowing faintly in reflected ring light. At the time it was taken, in September 2017, scientists already knew the moon had plumes. They already knew there was liquid water underneath the ice. What they didn't know, what they couldn't have known yet, is just how chemically rich that hidden ocean actually was. And the answer to that question wasn't sitting in the final images at all. It was buried inside archived readings from an instrument called the Cosmic Dust Analyzer, data that had been sitting mostly untouched since Cassini flew directly through one of Enceladus's plumes back in 2008, 9 years before the spacecraft's death, and roughly 17 years before anyone would fully understand what it meant. In October 2025, a new analysis of that archival Cassini data confirmed that the icy jets shooting from Enceladus contain organic molecules, the fundamental building blocks associated with life. That alone would have been a significant finding. But the real breakthrough was subtler and far more important. Scientists had already detected organic material in Enceladus's plumes back in 2018, but there was a nagging, unresolved question hanging over that discovery. Were those organic molecules actually coming from the ocean itself, or were they simply being created afterward, out in space? As ancient ice grains got bombarded by radiation for centuries, the 2025 research resolved that ambiguity entirely by analyzing freshly ejected ice grains and confirming that the organic material was present at the moment of ejection and originated directly in the moon's liquid water. Astronomy.com, astronomy.com. Read that again, because it's easy to skim past how significant that actually is. This isn't radiation-damaged debris drifting in Saturn's rings for centuries. This is fresh chemistry, straight out of an alien ocean, captured mid-flight by a spacecraft that had already been dead for 8 years by the time anyone finished the analysis. The pivotal flyby happened in 2008, when Cassini flew directly through the plume erupting from Enceladus's south pole, using its Cosmic Dust Analyzer to capture ice grains just minutes after they were ejected from the moon, striking the instrument at roughly 18 kilometers per second, over 40,000 miles per hour. That speed mattered enormously because at higher impact speeds, individual molecules could be identified more clearly, whereas at lower speeds, the ice simply shattered and the signal from water molecules drowned out the more delicate organic signatures scientists were hoping to find. In other words, an accident of orbital mechanics, or the specific angle and velocity of one flyby nearly 2 decades ago, is the reason we can now say with confidence what's actually inside that ocean. NASA space flight, NASA space flight. And what's inside it is not simple. The team identified entirely new classes of molecules never previously detected in the Saturn system, including aliphatic esters and alkenes, heterocyclic esters and alkenes, ethers, and nitrogen and oxygen-bearing compounds. Esters and ethers are particularly significant because on Earth they can form part of lipids, and lipids are essential to life as we understand it. This is not a vague, symbolic gesture toward the ingredients of life that gets thrown around loosely in press releases. This is specific organic chemistry with known biological relevance on the only planet we know for certain harbors life, showing up inside an alien ocean that a spacecraft first found hints of 20 years ago. NASA, spaceflight, University of Washington. But here's where it gets worse, in the best possible sense of that phrase. The organic molecules weren't the only secret sitting inside Cassini's old data. Just weeks after the Enceladus Organics paper made headlines, a completely different team, working with a completely different Cassini instrument, revealed something else entirely. And this discovery was about heat, not chemistry. New research published in November 2025 revealed that Enceladus is releasing heat not just from its already famous south pole, but from its north pole as well, meaning the moon is generating energy from both ends simultaneously. Why does that matter? Because a subsurface ocean doesn't stay liquid by accident. It needs a consistent source of internal heat to keep from freezing solid over geological time. This newly confirmed balance of heat could allow Enceladus's ocean to remain liquid for billions of years, long enough, potentially, for life to take hold and evolve. Science daily, science daily. Think about how that discovery was even made. Cassini didn't have a thermometer stuck directly into Enceladus's crust. Researchers instead modeled the expected surface temperatures during the moon's long polar night and compared those models against real infrared readings collected by Cassini's composite infrared spectrometer, ultimately finding that the North Pole was running roughly 7 degrees Kelvin warmer than it should have been if the moon were simply a dead, inert ball of ice. That excess warmth had nowhere else to come from. The only explanation is heat leaking upward from the hidden ocean itself, and the team calculated that flow at roughly 46 milliwatts per square meter, a figure that, spread across the whole moon, amounts to about 35 gigawatts of energy, comparable to the output of tens of thousands of wind turbines. Science daily. Science daily. Combine that new northern heat signature with the previously known energy escaping from the active South Pole, and Enceladus's total heat loss comes out to roughly 54 gigawatts, a number that lines up almost perfectly with predictions of how much heat tidal forces from Saturn's gravity should be generating deep inside the moon. The physics finally make sense. The ocean isn't a fluke. It isn't a temporary dying pocket of meltwater that happened to exist for a geological blink of an eye right when Cassini flew by to see it. It's being actively, continuously heated on both ends of the moon by a mechanism scientists can now actually measure and explain. Science daily. And even then, the archive still wasn't finished talking. Yet in work published in the Journal of Geophysical Research, Planets, a research team ran advanced supercomputer simulations called direct simulation Monte Carlo models on data Cassini gathered as it repeatedly flew through Enceladus's plumes. The goal was deceptively simple. Figure out exactly how much ice and water vapor Enceladus is actually losing to space every time it erupts. The results showed that the mass flow rates coming out of Enceladus are between 20 and 40% lower than what had been published in earlier scientific literature. That might sound like a footnote, a minor correction buried deep in a technical paper. It isn't. Every future mission that gets proposed to visit Enceladus, every calculation about how thick the ice shell is, how fast the ocean is losing mass, how long that ocean can realistically survive, all of it depends on getting these numbers right. And for years, the numbers were wrong. Science daily. Science daily. Think about what that means for the bigger picture. Scientists have been building models, writing proposals, and planning follow-up missions around Enceladus for the better part of a decade. And it took a spacecraft that had already been dead for 8 years, combined with supercomputer power that didn't even exist when Cassini was launched, to reveal that some of the foundational numbers underpinning those plans needed to be rewritten. These refined estimates now directly support planning for future robotic exploration of the moon. Science daily. That future exploration isn't hypothetical anymore either. These cascading Cassini-derived discoveries are directly strengthening the case for a dedicated European Space Agency mission built specifically to orbit and possibly land on Enceladus. Such a mission is currently being studied at ESA and would likely involve an orbiter far more sophisticated than Cassini ever was, with a lander included as a serious possibility. The scientists leading that discussion put it in a way that's almost unsettling once you sit with it. Why risk a dangerous landing on unstable ice, when Enceladus is essentially handing out free samples of its ocean directly into space through its own plumes? ESA plus 2. Sit with that for a second. A moon, hundreds of millions of miles from Earth, is continuously firing pieces of its own hidden ocean directly into the vacuum of space, for free, no landing required, no drilling, no risk. And it has been doing this the entire time humans have had spacecraft in the neighborhood to notice. And there is even more sitting in the vault. Separate analysis of Cassini data revealed the presence of phosphorus locked inside salt-rich ice grains ejected from Enceladus, an essential chemical element for life that scientists had specifically been searching for and hoping to find. Laboratory experiments following that discovery indicated the concentration of phosphorus inside Enceladus's ocean could be at least 100 times higher than the concentration found in Earth's own oceans. 100 times. Not a trace amount, not a hint. An abundance. NASA. Linda Spilker, the same project scientist who once described Cassini's final images as entries in a farewell scrapbook, responded to this specific discovery by framing the real question ahead of us. Not whether the ingredients for life exist out there, because increasingly it seems they do, but whether life itself actually exists somewhere in our own solar system, and whether Cassini's legacy will end up being the thing that finally helps us answer that. NASA. It was the end of Cassini's ability to collect anything new. Everything that's happened since. The organic molecules confirmed in 2025, the heat signature discovered at the North Pole, the corrected mass loss calculations from supercomputer models, the phosphorus concentrations 100 times higher than Earth's oceans. All of it came from data that already existed, sitting quietly in archives, waiting for scientists with better tools, better questions, and more patience to come looking. One of the researchers behind the 2025 organics discovery said something that captures this perfectly, almost accidentally summarizing the entire hidden shape of this story. Cassini's orbiter was never really designed for deep, focused scrutiny of one specific object, and repurposing decades-old instrument data for cutting-edge astrobiology proved genuinely difficult, not least because of how hard the resulting archived data actually was to work with. In plain terms, Cassini wasn't even built to answer the questions it's now answering. It stumbled into some of the most important astrobiological evidence in the history of space exploration, almost as a byproduct of a mission designed for something else entirely. And it's taken almost 20 years of painstaking, unglamorous reanalysis for humanity to catch up to what its own spacecraft already handed us. Scientific American, which raises the uncomfortable question nobody has a clean answer for yet. If a single archived flyby from 2008, analyzed nearly 2 decades later, could reveal fresh organic chemistry straight out of an alien ocean, what else is still sitting in that same archive, unread, unanalyzed, waiting for the right question to unlock it? Even the lead researcher on the most recent breakthrough admits there are still certain signals in the Cassini data that scientists observe but do not yet understand. Scientific Americans, think about what that really means. There is data sitting on servers right now, collected by a machine that burned up in Saturn's atmosphere nearly 9 years ago, that scientists have already looked at, already measured, already recorded, and still cannot fully explain. Nobody knows what's inside those unresolved signals. Nobody knows if they're noise or if they're the next headline, the next Nature Astronomy paper, the next piece of evidence that gets us one step closer to finally answering whether we are alone. So here's where the story actually leaves us, and it is not a comfortable place to stand. Cassini's final images were beautiful, yes. A moon glowing in ring light, a giant orange haze hanging over Titan's methane seas, a monochrome frame of the exact patch of sky where a spacecraft chose to die. But the images were never the real story. The real story is the archive left behind, an archive that keeps producing discoveries years and years after the mission it came from went silent. An archive that in just the last 12 months alone has confirmed fresh ocean chemistry, discovered heat leaking from a second pole, corrected long-standing errors in how much material Enceladus is actually venting into space, and detected phosphorus concentrations that dwarf anything we have on Earth. A machine that died in 2017 is still making some of the biggest discoveries in modern planetary science in 2025 and 2026, years after mission control fell silent, and the engineers who built it moved on to other projects. An entirely new mission, one specifically designed to chase everything Cassini only glimpsed, is now being actively planned at the European Space Agency, built on the foundation of data an old, dead spacecraft is still quietly handing us. Which leaves one question hanging over everything, a question nobody currently has the tools to answer. If the ingredients for life keep turning up, one paper at a time, buried inside data from a spacecraft that's been gone for nearly a decade, how much longer until someone finds the ingredient that isn't just a building block, but proof of something actually alive? And when that day comes, will it come from a brand new mission, engineered specifically to look for it? Or will it come once again from an old archive, from a machine that's already dead, quietly waiting in storage for someone to finally ask it the right question?